Hey, geometry. So moving on to 6-4, still in quadrilaterals, we're going to change it up for some rectangles. So a rectangle is a parallelogram. Wait, that's not right. Well, actually, I mean, it is. A rectangle meets all of the conditions for a parallelogram, but we can be a little more specific about it. It is a parallelogram with 4 right angles. All right, so rectangles follow all the rules that parallelograms do. The opposite sides are parallel, and so on and so forth. We'll go through a bunch of that here, but we want to make sure we got right angles in all 4 corners, and a couple other properties show up as well. So all 4 angles are right angles in a parallelogram. We got that. Opposite sides are both parallel and congruent, as they are in parallelograms. That's the same. Opposite angles are congruent, as they are in a parallelogram. In fact, all 4 angles are congruent. Consecutive angles are supplementary, as they were in parallelograms, though here, I mean, they're the same. They're both 90 degrees, but they are still supplementary. And then the diagonals bisect each other, as they did in parallelograms. And this bit's new. Diagonals are congruent. So, KM and JL, those measures are the same. All right, so basically that's it for most of our properties here. Just kind of trying these different problems out with rectangles. A rectangular park has 2 walking paths as shown. So we got like crisscrossed paths here. You may not be able to see it super well, but we got crisscross paths going on. All right, and then PS is 180, so they tell us this is 180 meters, and PR is 200 meters. So this distance here is 200 meters. Find QT. So we can use one property that's new here. Diagonals are congruent. Ultimately, this is what we want to know, QT. So I know that QS, I'm going to jot this down just to kind of show some work, but QS is going to be equal to PR. And PR is 200. So I know that QS equals 200. So this length here is, and I'll try and do it out here, that length is also 200 because diagonals are congruent. And then diagonals still bisect, as they did with parallelograms. So QT is going to be half of that. So QT is equal to 1/2 of QS, right? Which is equal, 1/2 of 200, which is 100. All right, so QT, that measure is 100 meters. And that's using some of our diagonal properties. We really didn't need this measurement at all, this 180 over here. All right, another example. Quadrilateral JKLM is a rectangle if the measure of KJL right there, is 2x plus 4, and the measure of JLK right down here, is 7x plus 5. Find x. Figure out what x is. All right, so there are a few ways we could do this. We could use the fact that this is all part of a triangle with a 90-degree angle here, right? So this is one big triangle. So that's 90 plus this equals 180. Or you could just say these two are complementary. They add up to 90. So I could set up 2x plus 4 plus 7x plus 5. I could throw some parentheses on there, but it doesn't really matter since it's all stuff just being added. Equals 90 degrees. Or you could say plus 90 equals 180. Same thing. You could also bring this down here, right? Alternate interior. These are parallel lines. So 2x plus 4, this means this angle JLM would be 2x plus 4, and we could add them up to 90. We could bring this one that way. There are a few ways of getting there. But once we've got this, we can set up and solve. We can combine like terms. 2x and 7x is 9x. 4 and 5 is 9. So 9x plus 9 equals 90. So we'll subtract 9. 9x is 81. And so x is 9, and solve it that way. All right, moving on to the back, additional property here, diagonals of a rectangle. If the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. So remember we had all those rules where if the opposite sides were congruent, then it's a parallelogram. If opposite sides are parallel, if opposite angles are congruent, and so on. Diagonals bisect. We had a bunch of different ways we could prove that it was a parallelogram. Now we've got if the diagonals are congruent. That proves that if it's a parallelogram, it's a rectangle. Now not all diagonals congruent, right? If you had diagonals that weren't part of a parallelogram that are congruent, there's a whole bunch of different shapes we can make with congruent diagonals. So it has to be a parallelogram first. If the diagonals are congruent, it's a rectangle. We also can show that, we have 90-degree angles for the corners as well to show that we are dealing with a rectangle. All right, Community Recreation Center has created an outdoor dodgeball playing field. To be sure that it meets the ideal playing field requirements, they measure the sides of the field and its diagonals. So that's actually something you do a lot in like construction. If you know you're supposed to make a rectangle, measure the diagonals, because you can make all four sides right, but it's just a parallelogram, right? Your things might be bent a little bit, but if you measure the diagonals, you'll know you actually have a rectangle, which we tend to like for construction an awful lot. So to be sure the ideal playing field, they measure we got AB is 60, so we got 60 up here, BC is 30, CD is 60, and AD is 30, so we got those measurements. AC is 67, so this measurement there, I'm going to try and bring it out here, is 67, and then BD is 67. So this measurement is 67. It's really hard to kind of mark those diagonals where they overlap each other. So I don't know if this is the best way to do it, but that's what I'll do. All right, explain how the Recreation Center can be sure that the playing field is rectangular. So first, we can say that it's a parallelogram because opposite sides are congruent. So we know that it is a parallelogram. A parallelogram, I'm just going to kind of draw the picture of a parallelogram because opposite sides are congruent, right? So 30, 30, 60, 60. So because of that, we know we're dealing with at least a parallelogram. And then on top of that, we know that it is a rectangle because the diagonals are congruent. And I'm going to throw in here an also, are also congruent. Let's finish over there. Because it does have to be a parallelogram, right? Just congruent diagonals can exist for other shapes where it's not a rectangle. You can kind of think that through, that, yeah, two of the same diagonals could make a whole bunch of shapes. Yeah, not if it's a parallelogram. All right, last bit, we're going to get into some coordinate stuff. So we've got some vertices for a quadrilateral. We're going to determine whether that's a rectangle using distance formula. So let me pause up and get some points on our graph. All right, here we go. So we're going to do distance formula. We could go about this in other ways where you could show this as a parallelogram by showing that opposite sides are parallel with the same slopes and consecutive sides are perpendicular, which means we form 90-degree angles, right? So we could check for rectangle with that way with slopes, among a couple other options. But we're going to focus on just doing distance formula. So before, again, I could prove the diagonals are congruent, but that's not enough. I need to show that this is actually a parallelogram. So I'm going to kind of fly through here, hopefully, and just show that these opposite sides have the same distance. And so I'm just going to kind of shorthand it and do some like Pythagorean theorem. So horizontal distance here from S to P, it's 2 over, so 2 squared, and then 3 up. 2 squared plus 3 squared, and then when we take the square root, that'll give us that hypotenuse. And so we really don't even need to take the square root. We can just write down 4 plus 9, so that is 13. Square root of 13 will do. I don't need to know what the decimal is. We could figure it out, but we don't need to. So I'm going to hop across to QR and verify that that is the same. And these numbers are going to be familiar. 2 over, 3 up, so 2 squared plus 3 squared. Yep, that's the same stuff. It's going to be the same thing. Opposite sides are congruent. All right, so then next we can move on down to, or move over to our other 2 points. So I've got like PQ is, and so we want to get our horizontal distance. So going across here, so I'm going to go horizontally. I'm dropping down till I get to Q. I guess you could go the other way. I'm going 1, 2, 3, 4, 5, 6 over, 6 squared, plus vertically, we go 1, 2, 3, 4, and that is down, but we really don't care about the sign. I mean, I could throw a -4, but it's getting squared, so it's going to all end up positive anyway. So 6 squared is 36, plus 16 more. 36 plus 16 gives us 52. And so we got square root of 52 for that one. Let's see if we can replicate. Go in with SR and verify horizontally. We're traveling 1, 2, 3, 4, 5, 6. Sounds good. Vertically 4. 1, 2, 3, 4. So 6 squared plus 4 squared, take the square root, and we get the square root of 52. Whatever that number is, opposite sides are congruent. So I've established a parallelogram. So then, finishing off with distance formula, I need to show that my diagonals are congruent. So these ones will be the same, but if it is a rectangle. But we got to actually calculate them both. They're not going to be the same numbers like before. So let's start with, I'll start with SQ. So SQ is horizontally, we're traveling 1, 2, 3, 4, 5, 6, 7, 8. So we're doing 8 squared plus vertically 1. 8 squared plus 1 squared. So 64 plus 1 more. So square root of 65, whatever that number is. And then let's check PR. All right, RP, I wrote the R first. RP, is that congruent? And so horizontally, we're traveling 1, 2, 3, 4, right? So 4 across, 4 squared, plus vertically, we're going 1, 2, 3, 4, 5, 6, 7. So 4 squared plus 7. Does that work out? So, and again, a -7 doesn't matter, it's getting squared. So 49 plus 16. So that's 59, 65. All right, so 49 plus 16, 65, square root of 65. So the diagonals are congruent. And so we have a parallelogram. Or sorry, we have a rectangle. So right here, it was kind of therefore parallelogram. And then here we have diagonals congruent. Congruent. So therefore, we have a rectangle. And just to remind you, the 3 dots means therefore. If you haven't seen that before, you can write out therefore. But yeah, just a little shorthand there. Dealing with rectangles.